Now that we understand what the heat capacity is, as well as some basic deviations that we could discuss from the ideal gas law and what those look like, let's now discuss the final topic that we'll touch on in gases, which is partial pressure, as well as Dalton's law of partial pressure. The partial pressure is actually quite simple. It's simply defined as the total pressure of a gas times the mole fraction of a particular type of molecule in that gas. We'll call that mole fraction X for this equation. What this is referring to is, suppose, for example, you have a system with more than one type of gas in it. So, for example, I have here in this piston not just nitrogen, but also some carbon dioxide. Suppose I have 5 moles of nitrogen and I have 15 moles of carbon dioxide, and I know the total pressure of the system is 1 atmosphere. How could we define the partial pressure of just the nitrogen or the partial pressure of just the carbon dioxide? We do that very simply by saying, for example, the partial pressure of the nitrogen is equal to the total pressure in our piston times the mole fraction of the nitrogen that's present. In other words, how many moles of nitrogen are there divided by how many moles of gas are there in total. So we divide 5 for the 5 moles of nitrogen, divided by the total number of moles, which is 5 for nitrogen and 15 for carbon dioxide. And we get a ratio, a fraction, of the total amount of pressure that's present in this piston of 0.25 atmospheres as the partial pressure for nitrogen. We could do the exact same thing for the carbon dioxide and say that the partial pressure of the carbon dioxide is equal to the total pressure, 1 atmosphere, times the fraction of moles that are made up by carbon dioxide, which in this case is 15 moles divided by the total number of moles, 15 plus 5, this time arriving at an answer of 0.75 atmospheres. Dalton's law of partial pressures is very simple. It simply says that by definition, all of these partial pressures, 0.75 and 0.25 in our case, when you add them together, gets you back to the total pressure of your system, which in this case, of course, works. Adding 0.75 plus 0.25, we arrive back at the total pressure of our system of 1 atmosphere. Let's do a quick example of how we use partial pressure in Dalton's law. Suppose you have 10 moles of hydrogen gas with 5 moles of oxygen gas, and then they react to completion to form steam, basically making some water molecules. We could ask if the pressure in the system is the same before as after. What is the ratio of the total pressure of the oxygen in the partial pressure of the oxygen, the O2, in the final configuration after we've finished reacting, to the partial pressure of oxygen in the initial configuration before we've reacted? So just use the definition of partial pressure here, as well as some basic stoichiometry to make sure you get the numbers of the hydrogen and oxygen correct, and see if you can find this ratio of the partial pressures after to before. If you've done this problem, which I highly recommend, it should look something like this. First of all, we have to understand that we have an equation of hydrogens reacting with oxygens, and this is going to form steam. And the reason, and this is a good review of the chemistry, that we have the numbers that we have here, is that it takes 4 hydrogens with 2 oxygens to create 2 water molecules. And again, you can compare these numbers here. We have 2 hydrogen 2s, which makes 4 hydrogens, which is the same as over here. And we also have 1 oxygen multiplied by 2, which is the same as the 2 oxygen atoms here. What we have in this problem is, not 4 moles, but 10 moles of hydrogen reacting with 5 moles of oxygen, so that the entire initial number of moles is 15 moles. The question we have to answer for ourselves is, after all of this has reacted to completion, how many moles total do we have at the end of the day, and also how many moles of oxygen do we have at the end of the day? So let's do that. We have to be careful here because it's not as though all of these 10 will react with all of this 5. Notice for that, for 1 oxygen molecule, we need 4 hydrogen molecules, which means that if we used all 5 moles of our oxygen, we would need 5 times 4, or 20 moles of hydrogen. But we don't have 20 moles, we only have 10 moles, so that means we can only use half of our oxygen. So keeping this in mind, we remember that we have 1 mole of O2 for every 4 moles of hydrogen. That means we will only have 10 over 4 or 2.5 moles of oxygen used. This means at the end of the day, we in fact have 2.5 moles of oxygen left over, because starting with 5 and only using 2.5, we have 5 minus 2.5, or 2.5 moles of oxygen left. We will also have 5 moles of H2O, which you can see probably best by looking at the number of moles of hydrogen. If we had 10 moles of hydrogen, and we're using all of those up, where we need 4 hydrogens per 2 H2O, then we only get half of 10 moles, since we get 2 H2O but need 4 hydrogens, giving us 5 moles of H2O. This is our final system. The total number of moles in this system is 7.5. And now we know exactly what we need to compare. We're comparing this final system, 2.5 and 5 making 7.5, to this initial system, 10 and 5 making 15. So let's write those down. We have the partial pressure of oxygen in the initial system is equal to the total pressure of the initial system times the mole fraction of oxygen, which is 5 for the number of oxygens, over the total amount of oxygen, which is 15 here. These are both moles, so this fraction is just a number. And since 5 over 15 is 1/3, the partial pressure of the oxygen is 1/3 of the total pressure. We can do the same analysis for the final situation, and now use this box, which tells us that we have the total pressure times the mole fraction of oxygen here, which is 2.5 for the number of moles of oxygen, divided by the total number of moles, which is 7.5 in our final configuration. Again, the units of moles will cancel here. And 2.5 divided by 7.5 is in fact also 1/3 of the total pressure. The ratio then, which is what we're looking for here, of the final partial pressure of oxygen to the initial partial pressure of oxygen, is simply the ratio of these two quantities, which both happen to be 1/3 of the total pressure. The final important thing here to note is that these two pressures are identical, and this is told to us in the problem that after the reaction we have the same total pressure that we had before we started this. And so this in fact is equal to 1. So in this particular case, the total reaction does not change the partial pressure of the oxygen in the system, and in fact the partial pressure of the oxygen in the system stays the same. This wraps up our discussion of partial pressure, which also wraps up our discussion of gases in more complicated systems and some more complicated gas dynamics. And so we finished with the gas chapter and are ready to move on to some other more practical systems that we'll be discussing in this course. Thanks for listening.